another class coming in, I'm not used to getting pushed out, so we moved here. And for this quiz, what I did is I graded very leniently. Then, at the end of the day, I gave you 2 extra points. So it's out of 10. I didn't check the averages, but I apologize. I try to make these things up to be about 10-minute quizzes and give you 20. But sometimes it doesn't work that way. I know the ones with this kind of calculations cause a lot of people problems. So what I'm going to do is just hand them back. Now, if you look on OneNote, the answers should be up there. Did you all see the solutions to the quiz? Those are accurate, and they're worked out with OneNote, with MathCAD on the paper. If you have questions, please ask me about it. The only thing that people messed up on, overall, in my opinion, was thank you very much. The calculations for ZN, that was the thing. There were a lot of people that had trouble doing that, or they weren't sure how to do it. Other than that, most people did pretty well. So remember, that raw score is going to add 2 points to it. Now, I try to upload my grades to Canvas, and I kept getting this message that my header is wrong on this comma delineated CDS files that you have to upload. I'm going to try to straighten that thing out when I get from my office in a bit. Anyway, that's sort of the story. And let's see, any questions about anything up to this point that we did? Because on Friday, what we were doing is antennas. We did the short dipole, right? All right. What I want to do, I'm going to do a quick recap of that, and then this is the age-old problem of marketing world. And then what I'm going to do, I'm going to take you through some of the ways that we actually assign figures of merit to antenna performance. So first, for the short dipole, the idea is this. If you have an antenna, the total weight is L, and for a short dipole, L has to be less than lambda over 10, approximately. That's not an absolute prediction. When you get that, basically the current distribution on this antenna will be the same in magnitude everywhere. It'll vary with time, but it'll be the same magnitude. So if you have a current I on this antenna, the way I like to do it is come out a distance R. Here we have an angle theta, and usually in Dr. Whitworth's book and most books, they orient the antenna in the vertical direction, the Z direction. Now it doesn't have to be in the Z direction. The real thing that's important is the angle measurement from the axis of the antenna to R. Y'all follow me? That's the key. And from that, if you're out a distance R way, you're going to get an electric field that's equal to J eta beta times L times I naught, whatever the magnitude of the current is, over 4 pi R. Then it's going to be times e to the minus J beta R, and then it will have the sine of theta. And this will be in the A theta direction. This will be volts per meter. Now I'm just repeating something I said on Friday. So I want to take you from where I was and kind of just make sure everybody's on the same page. Y'all with me? Now, if I have that E field, there's also, this is at a distance R away, there's also a corresponding H field. And the H field is given as simply, really, the E field magnitude over eta naught, but it has to be orthogonal to it. Everybody understand that, class? And there's one other condition I didn't say yet, but I will in a second. So the only thing we do is get rid of eta, and we have J times beta times L I naught over 4 pi R times e to the minus J beta R times the sine of theta, but now it's in the A phi direction. Y'all with me on that? It's got to be orthogonal. All right? After that, I have to make one statement too. We talked about the far field condition. Do y'all remember that? So we have, this is for the far field. Far field. And when you're in the far far field, you're at a distance r that's greater than lambda over 2 pi. So that's the assumption, we're that far away, at least. And you can see as the wavelength gets longer and longer, you have to get further and further away. Everybody okay with that? All right, now, that's, I'm going to do the power density too, because on Friday we also talked about the power density from this, or the average power density. And the way I like to get it, you can take, it doesn't matter, you can say it's 1/2 magnitude of the E field squared over 8 naught. This is far field now, in the AR direction. Or you can say power density PF is equal to 1/2 times 8 naught times the magnitude of the H field squared in the AR direction. Either one will get you there. The reason I do it this way is because E and H are related by eta. So E over H is eta. Now, the only reason I put this one down here is because this one's a little quicker to calculate. You know, if you do this one, you're going to get an eta squared on top and an eta on the bottom. You're going to mess with it. That's it. And what actually happens is you're going to have some P max that I'll mention in a second. So I have 1/2 eta naught. And then I have to square H. Well, it's a magnitude too, so the phase goes away. That means I have beta L I naught over 4 pi squared. Then I have 1 over r squared. Then I have sine squared in the AR direction. And that would be in watts per meter squared. You can see here, we can go ahead and square this terms out. You can get beta squared, L squared, I naught squared. And this would be over 16 pi squared times 2, or 32 pi squared. You can do all that, but this is essentially it. Y'all follow me? That's it. That will work. Now, what most of the time is smart to do is take all these constants right here and just call that some P max. Y'all follow me? So create a new constant, and I do that all the time. Called P max, and that's equal to, I'll leave it as that, 1 over 2 times beta naught, then it's times beta L I naught over 4 pi squared. Just leave it as that, and that, therefore, now my average power density to be rendered is simply P max as such. It's really, it's not quite exactly right, but use that, then it's going to be times sine squared of theta over r squared, and this would be in watts per meter squared. There's something I want to mention about this. When you look at that, you'll notice it falls off as 1 over r squared. Power density in the far field from any antenna will always fall off as 1 over r squared. The thing that changes the profile, you might say the focusing ability or the gain of the antenna, is the angular variation. There it's a sine squared of theta. So where's sine squared going to be a maximum? When theta is 90 degrees, right? Because at 90, the sine is 1. When theta is 0, the sine of 0 is 0, and the sine of 180 is 0 as well. What it's really telling you is the power is radiating straight up or straight down. I mean, nothing's radiating straight up or straight down. It's all perpendicular or broadside to the antenna. Can everybody follow me on that? And this is a short dipole. It'll hold true for a half-wave dipole too. So that's the average power density. Now the next thing I'm going to tell you about is I want to use this as to work into something that where the metrics of the antenna, a measure of the what's called goodness or the ability of the antenna to focus power comes in. And it's called a gain. How many have heard of gain or directivity of an antenna before? One person, two. I don't know if you get it in any of your other classes, but it's an important concept. So when we talk about, and I can't write past that, so I'm going to come back over here. By the way, can somebody scoot down and see if there's anybody hanging out there? I figure a few people didn't look at their email. Okay. And just set it down this way. So now the next thing I'm going to tell you is this. there's something called directivity. And directivity is really the ability, it's a measure of how well this antenna can focus energy, or how much better it is than an isotropic radiator. So first I'm going to talk about what is an isotropic. Nobody's done that? I'm missing a lot of people. Where are the extra quizzes? Has everybody got their quiz? You have it? Can you pass it over that one? If you haven't got it, raise your hand and send it to you. And then pass up all the extras to the front, if you don't mind. So, first thing I'm going to do is you have to talk about something to compare the antenna, your antenna to, in terms of performance. And that's an isotropic radiator. So, first thing, when I talk about isotropic radiator, what I'm really talking about is something that has no focusing ability whatsoever. Is that air conditioning on, by the way? Yeah, thank you. I mean, is that air conditioning on? I'm not feeling any airflow. I'm trying to keep a fair amount of airflow until this COVID thing has died down. Alright, so an isotropic radiator means something that has no focusing ability. Think of the sun, for instance. The sun, well, we could get in an argument about that. Or a candle. It pretty much throws light in every direction the same way. Y'all follow me? So for an isotropic radiator, whatever it is, if we come out a distance r away and we're transmitting a total power P total, or P, call it P transmit, right there, then the power density, P av, is just equal to the total transmitted power divided by the surface area of the sphere, and that would be in watts per meter squared. Does that make sense to everybody? Right? I mean, if you take total power transmitted and go through the surface that all that power is flowing through, which would be a spherical surface, that would be the power density, watts per meter squared. You all agree with that? And the surface area of the sphere is 4 pi r squared. Correct, class? Everybody okay? So this is an isotropic radiator's power density. And they just, in Dr. Whitworth's book, he calls this P-ISO. That's it.
What's the subscript on the power right there?
Here?
No, over on the top, on the numerator.
This?
Yeah, that.
Transmit. It's just transmitted power.
Okay.
And it would be in watts. Total transmitted power. So, Whitworth's book calls this the isotropic power density. And the definition of directivity, and directivity in general is a function of angle, but it's never a function of R. So it can be a function of theta and phi, and it's equal to the power density that your antenna will have for the same total amount of radiated power. So it's P av of your antenna, whatever it is, over P av of an isotropic antenna at the same range. Y'all follow me? Just tells you how much better it is. We can translate that in terms of the electric field, because the electric field is related to the power, or the average power density by a squared operator. You have to square it. So this is also equal to the magnitude of the E field, and this would be the E field from your antenna, squared over the magnitude of the E field from an isotropic radiator squared at that same range. So it's really telling you how much better it is than something that doesn't focus. Do y'all follow me? Now, the way we calculate it is this. We're going to go ahead and calculate this directivity. I got to say something. The directivity itself is a function of angle, but it has a maximum value. So, first thing we're going to tell you how to calculate the maximum value, and I'm going to work backwards on it. So I want to give you what's used, and then I'll tell you why it's used. So the maximum directivity, or D max, D is a symbol for directivity, is simply given as 4 pi divided by, and it's called the beam solid angle. And I think Whitworth's book uses a sub P. Now what this is, the beam solid angle, you're gonna have to bear with me on this, is a surface integral of the normalized power density. Now I'll have to talk about that in a second. It'll be P normalized as a function of theta and phi, Then it's times the differential surface area on a sphere of radius 1, where it's times simply sine of theta times d theta d phi. And when you integrate this thing, theta goes from 0 to pi, and phi goes from 0 to 2 pi. Now that'll give you the maximum power density. So how do you get this normalized power density is the next logical thing to talk about. The normalized power density is this, and it's nothing more. If you take, like this is the average power density right here for a short dipole. You're going to forget about R. It will not be a function of radius. The only thing you do is find a maximum value of this, which happens to be P max, how convenient. Then you divide it in to the actual power density. So when I take a look at the normal, this is called the normalized power density. It's a function of both phi and phi possibly. What that is going to be the actual power density divided by the maximum power density, P max, at a given R. Now R will always go away. So for R's right here for the short dipole, and please pay attention to this. For the short dipole, you can see that P max is right there, right? So the average power density would be P max. I made sure I broke it out. And then it's times sine squared of theta, technically over R squared, but R squared cancels all the time, so you don't even have to put it there. Over simply P max, right? So that means it's simply equal to the sine squared of theta. Does everybody follow me on that? All right, you find the maximum possible value at a given range R, and then you divide that into the actual power density versus angle. Y'all follow me? So it's sine squared. Y'all see this, guys? It's just, this is just going to be sine squared of theta. If you can't read it, I'll put it up again. Sine squared of theta. Y'all follow me? How many do? All right? Now, once we have that, I want you to bear with me in this calculation. Normally, when I do this before, what I would do is say, well, the isotropic power density is the transmitted power over 4 pi r squared. Y'all follow me on that? That would be the isotropic power density at a given range R. Then what I do here is first calculate the total power radiated by my antenna, set it equal to P transmit, and then you might say, restate this in terms of the transmitted power density. Do y'all hear me on this? When you do that, you're going to get the same exact thing as I'm showing you right here. This is going to give you the maximum value of D, and when we take the maximum value of D, I'm going to do this calculation for it. We get the actual directivity as a function of theta and phi as D max simply times the normalized power density as a function of theta and phi. Now I want to do it for the short dipole first so you'll understand. Can everybody follow me on this one? Please just try to make this as clear as I can. So let me use this part of the board. So now we do this calculation. Be attentive here. This is one you're going to be required to be able to do. And you can thank God that your calculators do symbolic integration, because it saves you a lot of anguish sometimes. But I'm going to go through it the normal way. So when I calculate D max, this is for a short dipole. The equation says D max is 4 pi over, now I have a double integral of the normalized power density, which is sine squared, right? Times sine of theta, d theta, d phi. That's actually, they'll call that the differential solid angle, but I don't want to spend too much time just discussing different ways of talking about the same thing we use all the time. Think of this as the differential surface area for R equal 1. That's it, on a sphere. All right, now phi goes from 0 to 2 pi, or 0 to pi, pardon me. Theta, I'm sorry, goes from 0 to pi, and phi here goes from 0 to 2 pi. Y'all agree with that? All right, now I'm going to do it over here. And I'm just gonna work this integral. So I have the integral from 0 to 2 pi, and I'll put it back in, the integral from 0 to pi of, now look here, I got sine squared times sine theta. I'm gonna change sine squared into 1 minus cosine squared. Y'all follow me on that? So I'm gonna put 1 minus cosine squared theta here times the sine of theta times d theta d phi. Y'all following? Alright, so the outer integration is with respect to phi. Nothing in here is a function phi. So it just is integration of d phi is phi evaluated from 0 to 2 pi is 2 pi. Y'all see that? So I'm just going to put down 2 pi. Now, when we integrate the last part here, the integral, or the first part I should say, from 0 to pi, 1 minus cosine squared of theta times sine theta d theta. Now, for this one, we'll break it into two integrations. The first is this. We say 2 pi out in front. Then we're going to integrate from 0 to pi, and this is going to be sine of theta d theta. And then it's going to be minus the integral from 0 to pi of cosine squared theta times sine theta d theta. This is just a classic way of doing it. If you've had this in physics, the physics professors make sure they go through all the details of this whole thing. That way, for everything from then on, you'll be able to understand the normal steps. All right, what's the integral of sine theta? Isn't it minus cosine theta? Isn't that right, class? So if I take minus cosine theta, which would be here, I'll put it down. Minus cosine of theta, evaluated from 0 to pi. You all agree with that? Let me just get to the bottom line here. Isn't that the same thing as the evaluation of cosine theta from pi to 0? Right? Sure. So I can just do this. All right, what's the cosine of 0? 1. Right? What's the cosine of pi? So it's 1 minus 1 or 1 plus 1 or 2. Y'all follow me? I'm going to see that right there. Right. So I'm just going to erase that and put a 2 in here to save me a little trouble. In your calculators, this is one thing. This isn't even a symbolic integration. You can do this as an actual value. Your calculators, what are they? 89s, 93, Inspire. I believe they do these things in a trivial way. You can whip these things and get them done with no problem at all. Now, this is a little interesting, the last one. Some of you that had calculus recently in the last 18 months or so, you remember this one problem, because this is one that teachers love. This is what? A standard substitution. We let what? Cosine theta be equal to u, and therefore the derivative of cosine theta is minus sine theta d theta, correct? So that's what? It's a u squared du integration. Y'all follow me? So when I do this, I have minus the integral, and that's going to be, well, cosine is u, so it's u squared, right? And then, well, the derivative of cosine is minus sine, so this becomes plus, and then it's du, right? And since the substitution was u is cosine theta, when theta is 0, right? The cosine is 1, right? Right, because I'm doing the, maybe I should put this down. U is equal to cosine theta. Therefore, when cosine theta is 0, that's here. I have to substitute in the other limits now. That would be 1. Do you agree with me? Now, when cosine theta is pi minus 1, right? So it's minus 1. And now I have to do this. Well, some of you can already see what's going to happen. I have 2 pi here. Then I have 2. Now I can reverse these limits, make that minus, make that plus, and put a minus here, right? And now I have u cubed over 3, correct? When I integrate u squared du, I get u cubed over 3 at 1, right? So really I get this. Minus u cubed over 3, and it's from minus 1 to 1, 4, what's that going to be? Well, that's 2 pi, right? times 2 minus, and then it's gonna be quantity, 1/3, and it's times 2. Because it's minus, a minus 1 cubed is a plus 1. Y'all follow me? So now you're gonna have this, and what is this gonna end up being? That's 2 pi, right? And then I have, right, hold on. I think that's it. Hold it. So it's gonna be 2 minus 2/3, right? And that's 2 pi. And then you're gonna have that's 6/3 minus 2/3, that's right. And that would be 2 pi times 4/3, or 8 pi over 3. So then I come over to here, I evaluated this integration, which is this lower part. This is called solid angle. And that means my B max for this one is going to be equal to 4 pi divided by that, and that is 8 pi over 3. Or that's 3/2. And that's important, that's 1.5. That's the directivity of the short dipole. It's about 1.5 times better than an isotropic radiator if we had such a thing. Not a lot, you're not gaining a lot. Give you an idea of what directivities you can get with some high gain antennas or high directivity antennas. You can easily get 1,000 to 10,000. Alright, so they have much more focusing ability. It's saying you can get 10,000 times as much power density at the maximum or the focus point of the beam as you would with an isotropic radiator. And we're going to see with arrays, when you have array antennas, where you don't just have one good antenna, but you have a whole bunch in an array that's got a certain distance apart, then the gain goes up by the number of antennas squared for that array. So you can get enormous gains. Has anybody ever seen the movie Contact in here with Jodie Foster? You have? Anybody else? In that movie, they showed these huge deep space they're used for astronomy and astrophysics. They're microwave dish antennas, and they'll have like 10 by 10 at least. They'll have 100 antennas in there for deep space astronomy. And those type of things are super high gain, but they use them. This is the fundamental principle for an element itself. Okay, so that's D max, and therefore I can say the overall directivity, please write this one down, for a short dipole. So this is the directivity for a short dipole. Now you can say D is D max, or 1.5 times the normalized power density, which is sine squared of theta. And that is the directivity for a short dipole. Y'all follow me? Now I'm going to show you a few other things that are important. That directivity is very, very important for a lot of things, but it makes problems trivial. When you have an antenna, you know the directivity, you'll be able to do things very quickly. The directivity is a function of angle and has a maximum value. That's it. Something I have to say before I get into this too far is the directivity is for an ideal antenna. In other words, the total transmitted power is transmitted out there. Nothing is lost. You follow me? In the real world, antennas aren't perfect. You have some ohmic losses. Anytime you have current in metal, you get heating, and when you have heating, some of that power goes to heating. Y'all follow me? Everybody? So what they do is introduce the term gain. Now gain it takes into account all the losses. And gain, symbol G, is really the efficiency of the antenna. I'll call it EF, in this book he has it as EP. And then it's times the directivity. So gain can be no greater than the directivity, but it can be less, not a lot less. Typically, the efficiency of an antenna is 95% or better. So you'd note that E, what I have there, EF, which is the efficiency, it would be 0.95 maybe to 0.99. Y'all follow me? Anything less than that is horrible. And I have my own story about horrible. So I designed an antenna for NASA. That's paid a lot of money, not a lot, but enough money. And it was for a synthetic aperture radar, but ideally it would have had 8 antennas in an arm, or sorry, 8 evenly spaced antennas that are, they're called, they're really flat plate. Well, they're very low profile antennas, and for now, just call them circular patch antennas. There's more to this, all right? Got 8 on this arm, then at 120 degrees from that, another 8 and another 8. So it looks like a flower with 3 leaves with 8 antennas apiece. And we only, in this build, we only did the first, I think, maybe 6 elements. So we had 2, 2, and 2. And I designed it, and then we fabricated. I didn't fabricate it here. It shipped off. Somebody else built it. And then from the build, it went to Ball Aerospace for testing in a chamber, in an anechoic chamber. If you haven't seen one, walk with me after class and I'll show you one. It's right across from my office upstairs. And the guy called me and he said, listen, your antenna's got a standing wave ratio of 4, which means the efficiency is about 45%. Huh? Can't be. And I mean, I remember the design. I went through everything, the impedance matching, everything. Well, this guy was an electrical engineer. He wasn't just a technician. So he went in and he says, I'm going to just open the top of this thing and see if something's, amiss. And the guy who was doing the soldering, remember, a lot of technicians don't appreciate a lot of problems at high frequency. This is a 1.4 gigahertz antenna system. He left a huge solder ball. You know what solder balls are? You're not supposed to have it. Well, we had one that was causing this enormous inductance, that was causing a standing wave ratio mismatch, which is causing my efficiency to be horrible. Anyway, he went in and reheated that thing, removed it, and the antenna worked the way it should. But that was a scare of my life. Because, when you have a deliverable, if your deliverable doesn't deliver the specs, then you don't get your money. And that's not funny when you are out 30 or 40 grand at the end of it. So anyway, that was my little lesson about that kind of stuff. So one of the morals of the story is, before you just let something get tested, have a good look yourself. And that the guy at Ball Aerospace told me, this is the only time I've had an antenna test like yours where the person who designed it wasn't there. And I thought, this will never happen to me again. If I have to, I'll pay my way out there. NASA didn't want to pay my way. Anyway, I learned my lesson. So that's the story about directivity and gain. Gain is very important. Now here's why this is so important. Pay attention to this, you're going to like this. It simplifies life. I'm going to show you contrast. Were you ever told to minimize the amount of solder? I'm just curious about this. How many have actually done any soldering here? It used to be everybody did. I think most of you had. We were always told they had these solder suckers. I don't know what they use. And you're not supposed to have any more than the lightest amount of solder, and you're supposed to have your leads as short as possible. Whoever built that antenna apparently missed that lecture or whatever, because that's like as taboo as it gets, but it was done that way. So anyway, now how is this useful? I'm going to show you how this is so much better than so many other things, like calculating those E field equations just for a short dipole is a whole lot of J, eta, betas, and all that stuff. All right, so here's something. If I have an antenna, let's use a short dipole, but it doesn't matter what kind of antenna. And I have the directivity. Now for R's, for a short dipole, it's 1.5 times the sine squared of theta. Now, if I know I'm transmitting a certain amount of power, so I'm going to say the total transmitted power is trans P-tran here in watts. You okay with that? If I want to know what the power density is at a given range R, measured at an angle theta from the actual antenna's axis, then I can say this power density is just, now hear me on this one. You take the total transmitted power, that's your starting point. So you take P-tran, then you divide it by a surface area of a sphere. You should know the surface area of a sphere is 4 pi r squared. Do y'all follow me on that? So now I divide by the surface area of the sphere, 4 pi r squared. Now that's the power density that would be there if it was an isotropic radiator. Y'all hear me? The gain of an antenna is really directivity times efficiency. Tells you how much better it is than an isotropic, or worse in some cases if it's shooting up and down the axis. So then you take the gain of the antenna right here. That's a function of theta and phi, but never r. So now it's transmitted power over 4 pi r squared. Now my gain is 1.5 times sine squared of theta. And that's the actual power density. Do y'all follow me? Now this is in the far field, so that's the power density. I know I'm not supposed to write over there, so I won't. Alright, so that power density, let me go right here and do it. When I take P-tran over 4 pi r squared times the gain, and for a short dipole it's 1.5 times sine squared of theta. That's the power density. Well, what is the power density in terms of the E field? It's what? It's just 1/2 magnitude of the E field squared over 8 0. You all see that? That's the far field power density. So if we have the power density, we can easily get the E field just by taking this and multiplying it by 2 8 0. You all follow me? And then if we take the square root of that, we get E, the electric field in volts per meter. All right? Now, here's the thing that I gotta tell you about. Do you remember there was something called the radiation resistance of a short dipole? How many do? R rad for this thing was equal to 40 pi squared, well, I'm sorry, R rad is 80 pi squared, my bad. 80 pi squared, and it's L over lambda squared, right? Now that's the radiation resistance. The truth is a short dipole has a reactance that dominates, that limits current. And I'll get into that later. But if you want the total power transmitted, if I give you the current I here, I naught is a peak current, then the transmitted power density, or total transmitted power, would just be equal to 1/2 R rad times I naught squared. So you can get the total transmitted power, just, you have to know the current here, but in most cases, that current is very easy to obtain because the input impedance of all these antennas you'll face is well known. And I'll give you some of them, even for a short dipole, I'll show you what the total impedance is. So if I put any voltage out here, I can easily calculate this current. Now this is the one thing I want to make sure you understand. When you're dealing with that antenna and radiated power, the key thing is getting that current. After you have that current, you multiply 1/2 times that current squared times the radiation resistance, and now you have the total power, absolutely the total power that's actually transmitted. Take that total power, divide by 4 pi r squared, now you have the isotropic power density, then multiplied by the gain of the antenna, and you have that focusing factor. Now you know the real power density. With antennas, depending on the type of antenna, this gain will change all over the place. You'll see gains where you have 10,000 times a crazy angular function. Doesn't matter. They're well known and they're very easy to obtain. If we contrast this, remember how in the beginning class I said remember we just said we could get the E field for that one. If I wanted to, I'd multiply this by 2 8 0, like so, and then I take the square root of this whole thing, and now I have the E field, right? Remember in the beginning, the equation for the E field? j eta beta L over 4 pi r, right? E to the minus j beta r times sine of theta. There's a lot more that can go wrong with that equation, what I'm showing you here, because most of you have a fairly good appreciation for the transmitted power over 4 pi r squared as the isotropic power density. Then the only other thing you have to do with that is take it and multiply it by the gain of whatever antenna you want. And now you have the power density at a given range and angle. And from there, that power density always translates to be equal to 1/2 times E squared over 80. And you can get the E field. If you got the E field, you got the H field. So all that takes care of itself. Everybody with me on that? Wanted to just make it clear to you. Now, one other thing I want to do before I jump off of this short dipole. The 1.5, by the way, is the maximum gain for any small antenna. So a short, you'll see these loop antennas, small loop antennas, anything like that that has a small feature size relative to wavelength. But I gotta mention one other thing. It's beam width. So the beam width of an antenna is real important. Now, what they really are talking about is how wide the half power points, how much spread there is in the angular spread, the actual beam width between half power points. Let me explain this a little better. If my antenna is a short dipole and it's going this way, so it's this way, and I look at this, I would see if I plotted the actual power, normalized power pattern. This is sine squared theta. Well, if I plotted sine squared theta, and this would be the angle theta, then I would get this. It would be, this would be in a polar plot. Y'all follow me on this class? Really what you're seeing is something that looks like a bow tie, like this. You're really gonna have this. It'll be symmetric about the z-axis. So, the normalized power pattern at 90 degrees would be 1. Y'all follow me? If it's normalized, the biggest value you can have is 1. The place where the power pattern goes to 1/2, or when this distance right here, maybe I should do it this way, is 1/2. Remember, this length here would be 1. 1/2, this would be the power down to half, and this here. This is called a half power beam width. Or sometimes they would call it the 3dB beam width, because the actual electric field strength is down to 0.707, its peak value, but the power is down to 1/, it's really 1/2 the peak power. Y'all follow me? And that's the beam width. That's all it is. So let's just talk about the beam width for a short dipole. So I told you that this line here was proportional to sine squared of theta, right? Remember? So if you look at this, I mean, basically this thing's doing this kind of deal, right? So if I want the half power beam width right here and here, I could set sine squared of theta equal to 1/2, right? That's sine of what? 1/√2, right? What's the sine? Just take your calculators and tell me, when I have sine theta is equal to 1/√2, what's that angle theta? It's 45 degrees, isn't it? Isn't that right, class? 1/√2 is sine of 45 degrees. So that means this angle, I'll try to draw this a little better here. When I take a look at this, it means this angle would be 45 degrees, and by arguments of symmetry, this angle would be 45 degrees, right? That means I'm left with a beam width, half power beam width from here to here, of, well, it's 180 degrees from the North Pole to the South Pole. If I subtract 90 from it, I get 135, don't I, class? about. You agree it's 180 from here to here, and this is 90, right? It's waiting for somebody. Yeah, this is, so really what I would have is 45, and this would be 135, or this would be 90. So this is actually a beam width of 90 degrees. Do you all see that? I'm just saying that to see if you're thinking. You were. Now, and I gotta tell you one other thing. In the book, Wentworth's book, and other books will talk about the beam width. This is the half power beam width. That's the one they care about. There's another beam width, it's called the null to null beam width. And you're gonna see when we get into arrays and stuff like this, don't write this down, just listen. When you actually look at the normalized power density, you're gonna get stuff like this. And then you're gonna get a main beam like that. You're gonna get all sorts of little, basically, they're called, well, this is called the main beam, and these are called side loops. Think of this as the normalized power density, all right? Don't worry about that now. But then they'll talk about null to null. So this one goes to an absolute null and absolute null, and they'll take and find those values, and they'll say that's the null to null beam. We don't care about that most of the time. We care about half power beam. The only time they want null to null is when they're doing beam steering things with array antennas. But right now, don't worry about that. He'll mention it, he'll scare you with it. Don't worry about it. It's half power all the time, okay? Half power beam width. And you can get that from the normalized power density. So now I covered beam width, I've covered directivity, all relating to a short dipole, but all this stuff extends to the general, any kind of antenna. All the calculations will be the same. The next calculation, or the next antenna I want to bring up, because it's the way Dr. Wentworth's book does, is a loop antenna. And it's a small loop. And here's what I mean by that. This is lecture making sense what I'm doing. I'm trying to incorporate things that are meaningful, and I just throw a whole bunch of equations at you and show you how you get the field from halfway dipoles onto on dipoles, and not understand really the metrics that are important. Okay, so now I go back, and this is the small loop antenna. And I gotta say this, in his book, he doesn't bother solving for the fields by solving Maxwell's equations for this. And it is a tough problem, but here's what he has. If this is the x-axis, this is the y, this is z, he's gonna have a loop antenna, just a wire antenna, laying there. Now technically it's got a differential point there where you have a differential voltage driving, and you would have a current that would circulate around here, I. They're assuming the magnitude of that current doesn't vary over the loop. And the real thing that they assume is, he doesn't have this way stated this way, but if you have a radius A, if you think of the perimeter of that, the perimeter would be 2 pi A, right? That has got to be much less than a wavelength. Now technically, it's less than 1/10 of a wavelength. So it's like if you cut that antenna and straighten it out, that would be like a short dipole antenna, and that means that total length would have to be less than 1/10 of a wavelength. He has a different criteria. I think he has this in his book. Really what we're talking about is that the wavelength is very large compared to any of the feature sizes. The feature size might be centimeters, wavelength meters. Y'all follow me? That's orders of magnitude kind of deal. So when you have this, he goes ahead and he says at a given distance r in theta, he's going to do a hand waving thing about how to get the actual value of the E field. And here's why it's so hard. Because to do this, remember the way we did it for the short dipole, we first calculated the differential magnetic vector potential that would occur. Well, to do this one, there are special functions, they're called elliptic integrals, that are not something that we cover in this course. Just like this, when I told you about the cylindrical waveguides would require Bessel function solutions, here it would require elliptical functions, and there's more to that than just elliptical functions. He doesn't even bother. He just mentions some things about it. And then he says, well, the electric field out here and the H field I can give you, and so he does. I'll tell you what this is, because I wouldn't require you to memorize this.
So if you look in his book on, and I know I'm out of time, so just bear with me, I'm about out of time. In his book, the small loop antennas on page 445. But I just want to tell you this, the thing that comes out of this is, and I'll put the equations down for EMAG, but hear me now. Two things that are important. One is the directivity of this antenna is identical to the halfway, or to the short dipole. D is equal to 1.5 times the sine squared of theta. It's identical to the short dipole antenna. Y'all hear me? Very important to realize this. The second thing is, is that the radiation resistance for this is given. And there's a lot of ways to do it. In his book, there's a bunch of different formulas for this. Where is his thing? Yeah, this is on page 447, equation 8.65. It's 320 pi to the fourth S over lambda squared. Let me just write this down here. So it's 320 pi. You would not be required to have this committed to memory. Times S over lambda squared. S is simply equal to pi a squared. So it's a surface area of the loop. But I have to tell you, there's more to this. And I want to just finish the lecture here. That's the radiation resistance for one term. In other words, one loop. Most of the time, when you're dealing with loop antennas that are small, they'll have many 50, 100 or more. So the total resistance goes up by the number. If one loop had 100 ohms, 10 loops would have, if 2 loops would have 200 ohms, 10 loops would have 1,000 ohms. Y'all follow me? It's a linear addition, and there's not one, and I'll give you a formula about that. Next time, since I'm out of time, next time what I plan on doing is I'll do this in a little more detail, and I'll give you some formulas for it, give you some problems. I'm going to do the arbitrarily long dipole, the half-wave dipole, and then hopefully we'll get to the free transmission equation. Please keep up at this. Yeah.
Do you want to homework or you have how we solve it?
Yeah. I'll give you the equations for multiple loops, and in the book he gives you the equations for the infield nature for that. What I always tell people, you'll see the problems I give you. Normally, just find total power, find out the radiation, the total impedance of the antenna, find out the current. From there, you take total power transmitted, divide by 4 pi r squared times the directivity, which is this. You got the power density, you get the E field from that. E field and H field from that. That's how I do it. I'll give you some problems. Thank you for coming. I hope this room is better.